the screen.
Right. Oh yeah, already. I guess we can start it. Okay, so we're extremely happy to have Moult visiting us from Yale today. And he's going to tell us about conformal colliders in the LHC.
Great, yeah, so thank you very much for the invitation. So somehow, even though I did my grad school and everything on the East Coast, I've actually never been to New York City before. So it's very fun to come down. So today I'm going to tell you about some work we've been doing over the last little bit about trying to bridge the gap between some developments on the more formal side, which go under the name of conformal collider physics, with real-world colliders like the Large Hadron Collider. And so in this talk, I'm going to try and not get too deep into the weeds on either side, and try and just give a kind of overview of how I think these techniques being developed on the more formal side will really help analyses and actually how one looks at data at the LHC, in addition to actually providing new concrete ways of calculating things. But I'm happy to discuss afterwards more details on either side of things. So just to start things off with a nice picture, so everyone knows when you have collisions at the LHC, you get all these kind of crazy sprays of particles, and the classical way of analyzing them is in terms of these jets, which are just some collimated sprays of energy that have some particular kind of direction and some energy. And so the way one can think of these is they're meant to kind of project to some, in some infrared and collinear safe way, to some underlying amplitude for a kind of n particle scattering. And so these are both kind of a useful thing from just a kind of pragmatic point of view, because they enable you to perform tests of QCD and to search for new physics. And so they're kind of like the bread and butter of the LHC. But in addition to that, trying to compute these higher loop and higher point scattering amplitudes has really been a driver of theory developments in quantum field theory. So there's all these nice kind of new ways of studying the formal aspects of these processes, which were driven by trying to answer these questions in a nice way. And so if we go back to these collisions, looking at these kind of angular distributions of just jets that are produced in the collisions is kind of the like 0th order amount of information that one can get from these, both just from like a pure data analysis perspective, because you're just kind of projecting it down onto some kind of very simple directions and energies. And also from a theory perspective, you're asking kind of a very simple question about what's actually going on. And so one thing which one could do to extend this is to look inside the actual structure of jets and look at, for example, correlation functions about how the energy is distributed. So instead of saying that this jet has just some energy and is pointing in some direction, you can actually look at the statistical properties of the energy flux that is deposited on the detector at infinity. And so this is something which goes under the name of jet substructure. And so its origin was something kind of very practical. Just kind of an experimental thing, which was very useful, namely that if you have some particles, say, let's say here I just randomly called it this Z prime, which is produced and which decays only into a jet, there's no way that you could identify this with standard analysis techniques. And so what you want to do is to identify that there's something interesting in the energy flow inside this jet, which allows you to kind of see that there was something in there and open up kind of new ways of looking for things. And so this was introduced in around 2008 and really kind of reinvigorated people studying actually from the formal perspective, much like these scattering amplitudes, how one could perform calculations and how one could understand the structure of energy flow within jets, motivated by these kind of phenomenological questions which one would like to try and answer better. And so what this does kind of very concretely is it shifts a little bit the problem from calculating S matrix elements, which is something one learns in kind of every quantum field theory textbook, to trying to compute properties of the asymptotic energy flux. So very concretely, what you want to think of doing is if I have my detector kind of out here at asymptotic infinity, I have a bunch of particles, I have a bunch of particles which go into this, and I can kind of get rid of all their information except for just the energy flow. And so what you get is kind of some two-dimensional distribution. So this can either be like, in this case, it's the cylinder, but this could just as well be the sphere. And so what you get is some kind of two-dimensional distribution, which you can think of some as kind of like a statistical, like two-dimensional field of the energy flow for this particular event. And so what one would like to do, instead of asking questions about the scattering energies and angles, is to understand statistical properties of the energy flux at infinity. And in particular, so you can of course do this if you did a very brute force calculation by computing some very complicated S matrix element and then computing from that the properties of the asymptotic energy flux. But what you would like to do is to develop some tools and ways of thinking directly about this energy flux itself. And so one kind of neat thing which developed, so it actually developed quite a long time ago, but then was kind of rejuvenated more recently by Hoffman and Maldacena, was that one can actually give precise field theoretic definitions for what one means by a calorimeter cell at a hadron collider. And so this is something which is actually kind of very intuitive, so it's just given by this, depending on your background, it's kind of an energy flow or ANAC operator. And so all you do is you take the stress tensor of your theory, you dot it into some particular direction, which is the direction of the energy flow you're looking at, or the direction of the calorimeter. So you integrate over all times, because you imagine just the LHC or whatever is just kind of running in the background, and you're just averaging over all the energy or integrating over all the energy that comes through, and then you move it off to asymptotic infinity. And so depending on your kind of background, if you're used to looking at collider experiments, you can really just think about this as like a calorimeter cell in your detector, or if you like a more kind of Penrose diagram, you can draw this to show that it's an integral over time as these kind of line operators on the celestial sphere. And so what this is very nice is it kind of poses in a very kind of sharp question what you're actually trying to do when you study jet substructure. Namely, you want to kind of produce some state, for example, of the LHC, and then you want to measure correlation functions of these energy flow operators in that state. So you can imagine, like, if you're measuring a 3-point correlation, you can imagine having kind of a calorimeter that just has only 3 detectors at some particular locations, and you want to compute how the energy is distributed on the sphere. And so this is very much an analogy to how you analyze, for example, the cosmic microwave background, but it kind of phrases in a very nice field theory language. And so from this, kind of what this jet substructure really is just the study of these correlation functions. And so these objects are made
over all of the collisions at the LHC.
Sorry?
Average over all of the
Exactly. So I'll show later. So the LHC one needs a kind of intermediate. So it's most clean if you think about something like E plus E minus colliders, where you really source things by a local operator. So then the state is very easy to describe. So to actually do it at the LHC, I'll show later there's one intermediate step where there's some form of kind of factorization which allows one to do this inside jets. But the cleanest thing, that's kind of a technicality because you're colliding protons. But the cleanest thing to think of is where this state is really just produced by some local operators, which is what you have in like E plus E minus. And we'll come back to how it's done in LHC a little bit later.
Should we think of this as all jets, or only Z boson jets of a particular energy?
So one can here it's just any state you want. So later I will do on some particular high energy jets when I actually show the data for the LHC.
But not on a single jet. It's sort of statistical properties.
Exactly. So it's an average, and this is the thing that's actually important, which allows it to be computable. Is that this object? So like, for example, like your engenderness or whatever, it's defined like if I give you a jet, it has like an engenderness value. Whereas this thing does not have a value on a particular, like if you have a whole bunch of particles, each one gives some correlations, and so it doesn't have like one jet does not give one value, and so it's an ensemble average over all the like jets of a particular type, and that's actually what allows it to be computable. Like that's why it's a true like correlation function and allows it to be computable in a much easier way. And so these objects are maybe a little bit unfamiliar to people, so I'll just try and put them as kind of like an intermediate between different things which are hopefully familiar. So of course for the LHC, what people typically study are amplitudes. And so the reason why one likes this is because one has asymptotic states. And so there's been a huge amount of work in understanding very nice properties of amplitudes. But of course the one problem is that they're not IR finite for massless theories. And so that's why one had to do this kind of thing where you cluster these into jets in some IRC safe way. And this is what kind of destroys at least the kind of very nice underlying beauty of the amplitude when you try to put it into like a cross section of the LHC. So then on the other extreme, if you're kind of, let's move the mouse. If you're, let's say, a condensed matter person, what you like studying are correlation functions of local operators. And so these are either IR finite or non-perturbably well-defined, depending on your kind of which subfield you're in. But the problem is that these do not have asymptotic states, and so that's not what you actually measure at the LHC. And so what these energy correlators are is kind of a hybrid between a correlation function and an amplitude. So it's kind of like a correlation function that involves asymptotic states. And so practically, this is actually quite nice because both the study of these correlation functions and amplitudes are very well developed. And so we can kind of take the tools from each side and use the kind of best of both worlds to actually make predictions for things that are kind of concretely measurable at the LHC. And so, however, this is kind of much less explored, but there's kind of a sharp upswing of interest both from the formal and phenomenological community in trying to understand these objects better quite recently.
Sorry, by asymptotic states, you mean the state psi that you wrote down earlier?
No,
That's not asymptotic.
Yeah, so by asymptotic states, I mean here just that you have something going off to infinity. So here, I mean, like here in the amplitude, you're trying to do with a gluon state, which is why you have our divergences. So I just mean some state that propagates off to infinity.
So it's not quite true that it's a asymptotic state because it is not.
Okay. Yeah, there should exactly. So there should be some.
Okay.
You're trying to measure something in infinity and project it onto these states, which is why you have problems. Yeah. Okay, and so what I want to do in this talk is to kind of bridge what has been going on in the kind of formal community with these conformal colliders and kind of actually make it kind of meet the LHC and show that we can really kind of start thinking about LHC data in terms of, for example, scaling behavior, which is dictated by certain properties of these correlation functions, as well as actually measuring kind of higher points. So I'll explain exactly what this is later, but it's a 3-point function of these energy correlators. And so we can actually start measuring the shapes and scalings of these interesting correlation functions of these energy flow operators inside high energy jets of the LHC to really kind of test interesting properties of these correlation functions of kind of interesting field theory operators. And so just as an outline of the talk, and I may, depending on the time, I mean, I'll adjust it. So the first thing I want to do is go through the kind of most basic prediction of these light ray operators, namely that they obey an OPE and therefore will exhibit some scaling behavior as you bring them together. And this is just like for standard local operators. And so we'll discuss a little bit the original prediction of this and then show that one can really just concretely test it in LHC data and extract, for example, exponents of certain operators which control the scaling. So then after doing the scaling, I'll go on to start measuring higher point correlation functions. And I'll show how these can be quite easily computed using techniques from scattering amplitudes, which are quite well developed. And then one can actually measure higher point correlation functions of the amplitudes. And so one can do some nice kind of conformal block decompositions of these and test certain properties of the kind of this light ray OPE, which I'll discuss in a second. And then depending on time, I'll just show a little bit what happens if you do this in a more complicated system, not vacuum, but something like the quark gluon plasma.
The first one.
Yeah.
The word jet in the title is in a way misled, right? Because you do away with jets because you're just.
So good. This is a very good question, which So what I would like to do is to do away with jets. So that's what I would, because from this theory perspective, they're difficult because you have to use some clustering procedure and project down. Exactly.
Right.
But to actually kind of trigger on high energy events of the LHC, at a practical level, one essentially has to use some form of jet algorithm. So one could do it recoiling against, like, let's say a Z or something, but most of the time it's useful just practically to first cluster the jet and so to make some sample of jets at sufficiently high energies. And then there'll be a kind of factorization where this state will actually be independent of what was used to find that jets at sufficiently small angles. And so I'll show later that there's a reason why these are cut off. So in particular here, I'm actually using jets of just over 0.5. And so you'll see later that something horrible happens once the correlation is kind of the approximate size of the jet. So I'll show this in more detail later. And so absolutely, so this part is independent of the jet that was used, and that's why it's kind of a nice field theory property and is independent of all those ambiguities. But just at a practical level, one has to go through that extra step. And I'll explain a little bit later how one kind of splits these pieces, but that's a very good question. Any other questions before I continue on? Okay, so scaling behavior in jet substructure. So the first question which I think is interesting to ask is why is jet substructure, or why are there any of these connections between what people are doing in the formal world and jet substructure? And the reason why is that often when one considers quantum field theories, what you want to look for is some form of kind of universal or scaling behavior. And so in particular, often what you have is some nice behavior as operators are brought together. And so this is most famous with this operator product expansion here, which predicts a particular scaling behavior with some exponents as you bring operators together. And so the thing that's very nice about this is you can do some kind of measurements, for example, with macroscopic systems. What you're probing are some actual kind of very nice, well-defined anomalous dimensions in the underlying field theory. And so the thing that's really neat about these energy flow operators is that they also admit an operator product expansion. So this is a non-trivial statement because they're these non-local light ray, or so they're integrated along a null cone. So it's a non-trivial extension of the operator product expansion, which was originally conjectured by Hoffman and Malacina, and then has been worked out in detail in a series of papers by this group of authors here. And so I'll explain in more detail what it precisely means later, but what it says is that you can take two of these calorimeter cells and essentially expand it over a more general class of calorimeter cells. So these are standard calorimeter cells, which are actually like what you have in an LHC detector, and then these objects appearing over here are some generalized form of detector, but they're not kind of what an actual experimentalist can create. But the idea is kind of the same, that I can take some general configuration of these energy correlators and expand them over kind of more general detector. And so one should think about this as kind of almost the reverse of the standard OPE, where you expand some general state in terms of operators. So here you're kind of expanding what you can detect in terms of some general class of detectors. And so what this predicts is that as you bring, for example, two of these energy flow operators together, that they exhibit a very nice scaling behavior here, which is dictated by the twist of the operator. So it says that as you kind of take these two calorimeter cells and bring them closer or farther in angle, that they'll exhibit a power law scaling. So I keep screwing up this. They'll exhibit a power law scaling, which is dictated by essentially the anomalous dimensions of particular operators in your theory. And so if one buys that one can actually do this efficiently, which one needs to work out how to do it in QCD, it's extremely nice because it allows a kind of completely different way of thinking about jet substructure. So instead of computing some kind of scattering amplitudes going off, you can just study essentially the kind of symmetry and operator product expansion structure of these operators and take some higher point function and kind of OPE it down and make predictions about what you should actually see without ever kind of talking about the internal perturbative structure. And so if one actually understands, yeah.
But this seems to be, if you said literally the twist of the operator, then it's independent of the angle between N1 and N2, right?
But
and so
no,
you don't mean to say that.
So this is good. So this is just like the normal OPE,
no.
right? So I have two.
N1 and N2 are vectors.
N1 and N2 are vectors, and so what it does is replace. So this theta is the angle between N1 and N2.
Oh, sorry, I think you said it was a twist. Oh, tau is.
So yes, the tau is the exponent. Exactly. So it's just like as you bring two operators together, you get the yeah. Okay, perfect.
One considers OPE between these E's and O's. You get new objects, so it's.
So I'll show later what you get, and so often, and so. For like the leading scaling behavior, I'll show later, it's a very simple OPE because you only have the leading twist two operators in QCD, and so you'll kind of stay in that class. At subleading twists, so this is actually like a convergent expansion, then you get more interesting operators, and this is not fully understood. And so later I'll show kind of perturbative results for higher point functions where you can actually probe the structure of what appears.
But a leading term it closes.
At leading term it closes. I'll show that explicitly, and so that's why it's for the like LHC where you just want kind of like leading scaling behavior at small angles. It's essentially like trivial to do this OP, and I'll show it just closes onto a like the twist two spin J operators, and it's you just iteratively do them, and it's very, very easy. And I'll show that concretely in a second. And that's what makes it efficient. And then beyond, so these are not fully like later I'll show this like EEE OPE where you start exciting more and more operators, and the full structure of what you get on the right hand side is not fully, it's starting to be explored a lot more, but it's not kind of completely understood, so you can do it in a fully rigorous way. But part of the kind of interest in doing these perturbative calculations is to better understand what is on that side, so that you could do it fully efficiently just from this definition. And so I like to use this kind of picture from quite a while ago when Malacina and Hoffman had this paper. So they kind of say that you should have all this kind of beautiful scaling behavior. And there was this discussion, which you can watch in the recording of his talk, between David Gross, Polchinski, and Malacina, where he kind of said they should exhibit all these nice scaling behaviors. And then Polchinski was like, why don't you just, or like this should have been measured, why haven't people done this? And then he kind of says, I don't really know, I think they haven't thought about this. And this was kind of forgotten and still remained true essentially until this year. And so this isn't quite the historically accurate answer, but it's kind of a nice picture to show. And so the kind of two actual reasons for why this wasn't done is that one is there's kind of this classical approach to studying jets, which kind of took off in the late 1970s and then was kind of never revisited, which is to kind of characterize jets essentially by their shape. And so there's this very famous like jet shape called thrust, where you essentially take some jets and kind of project them and have some measure of kind of how wide they are. And then there's this generalization of your n-sub-jetness, which is taking this to kind of more generic kind of n-jet configurations. And so this was the kind of language which is extremely popular for understanding jets. And so the problem is that these objects are not correlation functions because they're not defined as a kind of statistical ensemble. So they can be, if you try and expand what they are, you have to expand over an infinite set of correlation functions. And so there was this kind of divide between the language that was kind of proposed by Malacine and Hoffman and what was done at like a practical level, which was kind of a bridge.
There is a way of understanding the scaling properties from this shape analysis.
From looking at, so these don't exhibit nice scaling behaviors. These do not exhibit any form of power law behavior, and they're not controlled by the same operators in a nice way. And so these ones are much more complicated. So there's ways in perturbation theory of understanding them, but you can't make kind of generic statements like this OPE, which are true in kind of generic conformal field theory. So these are much harder objects to understand. And so one way of saying that from a formal perspective is that to compute this, you need to know all the endpoint, like the energy, or like you need to know the 2 point, the 3 point, up to the infinite point and combine them in some particular way. And so what these, instead of kind of just considering the like 2 point, the 3 point individually, which is more like what you do in when you start characterizing a CFT or something. And so these are actually very complicated from a field theory perspective, even though they're kind of more like it's intuitive to think about if you're just kind of, yeah, looking at pictures, and which was what was done in the like 1970s. So. And then the second approach, so there was actually someone who proposed these energy correlators at the kind of very beginning, which was then kind of swept away, is that, and one of the problems with them is that the low energies of kind of the detectors like at LHC, it was actually very hard to measure these higher point correlation functions because QCD is not a conformal theory. And so if you try and measure them, so this is some kind of simulation from a long time ago of the difference between the result on partons, which is where you could kind of compute it and might have some of these nice quasi-conformal properties, and on hadrons. And you can see in this small angle region, they differ by like a huge factor, and so this was kind of abandoned. And the other problem is that if you want to compute higher point correlation functions, let's say like 5 point correlation functions, if your jets only have like 5 particles, which they did at LHC, you're just going to be very sensitive to the fact you have kind of a discrete set of particles in your final state. And so the very nice thing, which the LHC allows me to do, is you now have extremely high energy jets. So you're kind of in this regime where things are very perturbative, and these jets have very, very many particles. So they have like 30 to 50 particles, and so you can start measuring higher point correlation functions, for example, like 3 or 4 particle correlation functions in a regime where you actually have kind of perturbative control and you're not just dominated by non-perturbative physics. And so it really makes a kind of huge difference for being able to actually extract some of these properties of these correlation functions, which one can compute in perturbation theory and actually understand using this operator product expansion. And so one thing which I'll do, and I'm just going to kind of say here, is that throughout the rest of the talk, I'll actually kind of test these predictions that we have on real world data from the LHC. And so the way that one can do this is because the CMS collaboration has released a sample of high quality kind of data, which one can just use for one's own purposes. And so this is something which is not very good if you want to, for example, like discover the Higgs. But if you just want to look at like jet properties, every event has jets, and so this is something which is actually quite good for kind of testing out these ideas. And so this was something which has been packaged in what is referred to as MIT Open Data, and this was provided for us by Jesse and Patrick. And so what it essentially allows one to do is that one can just kind of ask for kind of anything, and so I asked at like 2 p.m. and they're able to provide it later that night. So it's almost like essentially like a Pythia or some simulation, but you can just do it on actual real data and kind of test these things where some standard simulation doesn't actually work. And so it's kind of a very nice way of rapidly testing new theory ideas on real actual data. Okay, so if we want to do this on real data, what we have to do is to understand a little bit more concretely and how to apply this operator product expansion in QCD. And so
you've said something, you've answered clearly a question, but it's so counterintuitive. I want to ask again.
Sure, yeah.
So my question wasn't clear. Namely, I would have expected to find these correlations within events, not averaged over different events. Why should that direction, 1, 2, and 3 in totally different events? Or if you averaged over different events, I guess you would wash out the inherent so maybe you didn't know what I was actually asking.
Good. So there are so one is averaging over all events, but what you expect is that in like each event, these things will still be collimated at small angles, for example. And so what it is picking up is that because it's only doing the kind of relative angle between the things
in a given event.
Well, so you can imagine one thing which makes it a bit confusing is how one does it in practice versus how one could do it in reality. So the way one should think about, the cleanest way of thinking about it is if you had like an LHC detector, which really only had like 2 calorimeter cells. And then you just run like events and average over many times and then plot what you get as a function of the angle between those two. And you'd see that it would increase, or what I'll show, because of the scaling behavior, that the energy correlations would increase as you move the two things together.
That I believe, but at the same time, it seems like the signal would be much, much lower than if you did it event per event and then averaged. And the proposal of taking a single, very fine pixel gets rid of or at least changes the complaints about defining jets through cones. So it seems like it could have been a good proposal and more sensitive if you did it event by event. But maybe I should just.
So the problem is that event by event, one can't, like if you actually, one can do it event, so if you have like event by event, let's say like a jet has like 10 particles. And so what you actually get is then like 10 choose 2 pairings of this, which you put into like a histogram as a function of the angle. So is there, so this is why these things are a little bit confusing to think about. So let's say I had some like jet that had like 3 particles like this. So then if I'm doing my like 2-point correlator, what I do is I first take like this pair. This has some angle like theta 1, 2. This has some angle theta 2, 3. And then this has some angle like this, which is like theta 1, 3. And then what you do is you put this into some histogram as a function of the angle. So I get like one thing at theta 1, 2, one thing at theta 1, 3, and one thing at like theta 2, 3. And they're weighted by the product of the energies. And so if you actually look at it for like a given event, it has almost no information. So it would just be like these 3 bumps. And then what happens is as you like average over many, many events, it will like fill in to make some smooth distribution like this. And it's only the properties of the ensemble average over many events that one can actually predict.
I can see how maybe it's a semantic thing. It may become more clear later.
Okay.
But to the extent that you're talking about angles between depositions.
Yeah.
And not the absolute directions, which is how you sort of originally described it, then it makes more sense.
Yeah, so the problem is that how one practically does it, because you can't, like if I could build an LHC that just had 2 detectors, that's the cleanest way of doing it. So at a practical level, you're taking like pairs of those calorimeter cells and then doing it like this. And it's the same thing. It is a bit unintuitive, but if you look at it event by event, which we've certainly done, it just gets like essentially noise. And then it just like smooths out to a very nice distribution.
Once you accumulate all the events.
Once you accumulate.
But as a function of the separation.
As a function just of the separation.
Function of the absolute positions.
Not as a, so you can do it, it is also interesting as a function of the, less so the LHC, but like in E plus E minus, it's interesting as a function of the absolute position. At the LHC, we'll just be doing it relative, and we'll average over. So like I'll say in a second, there's like operators that have spin, and so we'll be averaging over those and just looking at relative directions. Yeah.
Okay, thanks, that's perfect.
Yeah. Okay, and so what we want to do is to actually make this concrete for the LHC. And so the reason that we can do this very efficiently is that this is meant to be an actual full kind of expansion, but if we just want to predict the leading scaling behavior, for example, like you do in some condensed matter system for the critical behavior, all you need is the operators that have leading twist. So those are the objects which will dominate the scaling behavior. And so those in particular are these twist2 light ray operators in QCD. And so the nice thing is that if you look in, for example, Peskin, it just shows what are the local operators that have twist2. And so you have two of these which have no transverse spin. And so they're characterized by this, what is called a spin, which is not the transverse spin, but it's just the kind of collinear spin. And a transverse spin, which a weak coupling can only be j equals 0 or 2. And that's kind of how they're spinning against their direction of they're going. And so you have these local operators, one for quarks and one for gluons, which are characterized by the number of derivatives in here. And then you have one object which has some transverse spin. And so what one can do, just like the stress tensors, you can take these and smear them along null infinity. And so very loosely speaking, what you can think of these as some detector which detects a quark and one which detects a gluon with some given energy weightings. And so what one is going to try and do is expand these more general excitations over particular combinations of operators which can detect either quarks or gluons. And so related to your question here is that if I'm only interested in the relative angles and not their orientation to anything, I will ignore or average over these polarized operators which contain some part of the normalization, and these are unpolarized operators. And so what is very nice is that then if I do this OPE, all I ever get are these two classes of operators shown here. So just these twist2 spin j operators, and their anomalous dimensions will control all the leading behavior of jet substructure observables. And so now in perturbation theory, this is related to your question, you can just very explicitly do this OPE, and I'm not going to give the explicit formulas, but there's just some OPE coefficients which you can compute in perturbation theory. And if you combine two of these energy flow operators, you get a twist2 spin 3 operator shown here. And if you OPE with a twist2 spin j operator with another one of these, it just increases the spin by 1. And so these are something which is kind of practically extremely easy to work out. And there's just perturbatively computable coefficients, which you can just plug in. And so what it means is that if you're just looking for the general scaling behavior, you can just OPE these things down, and essentially you just get into expectation values of these twist2 spin j operators. And so now this is again related to your particular question here, that ideally one would like to evaluate these just in some particular state. And so the LHC, this is a bit difficult because you actually have to identify some particular jets. And so what one can do is to prove some form of a factorization theorem, which I won't discuss in detail how this is done, but essentially what it shows is that you can split this up into kind of something producing some particular jet state, and then evaluating the correlation function in some highly boosted quark or gluon state, which is some expansion of what these jets mean. And so there's some like rigorous expansion that one can prove, where you can kind of disregard all the complexities and really just evaluate these energy correlators in some particular choice of highly boosted quark or gluon states. And so that's some technicality of kind of putting these into the LHC, which I won't go into too much detail, but just this kind of builds on well-known techniques for computing things at the LHC. And in particular, this kind of final piece is what depends on the actual angles of the correlators, and all of the extra garbage is put into some kind of prefactor which computes the states. And that's something which it's like very ugly, but it can just be done once and for all, and then you compute these nice things in that kind of prepared state. Okay, so now you can actually go out and just test this using this data which was provided by the CMS Open Data. And so this is a plot of these 2-point correlation functions shown here as a function of, this is using some hadron collider coordinates, but this is just the angle between these two correlation functions. And you can see that it exhibits this kind of very nice scaling behavior here. And so these are just compared against two levels of perturbative calculation, which include kind of in the blue one, slightly more data. And this can definitely be done to higher orders in perturbation theory. And so the thing which is at least kind of very nice to me is this is a very nice illustration of the universality of the OP limit in quantum field theory. So in these LHC events, you have all this kind of like stuff going everywhere. But if you look at this very specific question, you get a perfect kind of agreement between the real data, and there's been nothing done to it, and the predictions from this OPE expansion. And so because of this kind of universality, it really allows one to do a lot of new calculations in this very complicated LHC environment without having to describe all the extra kind of garbage that's going on. And so the other thing which is really neat, if one actually trusts this OPE, and it does work, at least for this leading twist, is that it predicts how the scaling behavior of higher point correlation functions scale. So one can take, for example, like a 10-point correlation function, which is, or the here is just shown 3, and you can ask how it scales as a function of its overall size. And so this is just like a scaling of like an n-point function in a conformal field theory. And so it will, in general, exhibit some anomalous dimension, which is dictated by the twist2 spin j operators as you change them as a function of size. And so if one normalizes to the 2-point, this is something which would be, they would scale exactly the same at the classical level. And so what you're doing is essentially just isolating the difference of anomalous dimensions. And so the reason why this is interesting is essentially, so here I show these ratios in LHC data compared with our calculation for the 6-point, 5-point, 4-point, and 3-point. And so, for example, for a 6-point correlation inside a jet, this is something which is impossible to compute in perturbation theory right now directly, but because of this OPE, you know exactly how it scales because you just need to know a particular anomalous dimension. And so you can see that each of these exhibits this nice scaling, which is just essentially the spectrum of these twist2 light ray operators in QCD. And so it exhibits some kind of general features that people have seen of these ready trajectories for these operators. So in particular, it's monotonic in the spin, which is just saying it increases as a function of the anomalous dimension increases as a function of the spin of the operators. And so you can really kind of image directly the spectrum of anomalous dimensions, which are controlling the kind of formation of the jet. And so it gives you kind of a very different way of understanding what is going on inside a jet.
So the result of access.
So this is essentially, you can view it as the size. So I can fix let's say an equilateral configuration. And so it's strictly speaking the longest side. So this is just something done for data analysis, but it's just the overall size of the correlator. And so it's just in a way that's, so you can show that it's independent of the particular shape, this overall scaling. And so this is just, you can take it to be like the largest side. That's what's done experimentally, which is why this is shown.
So there is a systematic discrepancy, which I'm sure you've noticed, between the solid lines and the data points.
So that's coming in here.
And also at the highest. I mean, it's just like the tilt isn't quite right.
The tilt is not quite right, absolutely. And so this is something which, so we can compute, I think this is something that will become better. So we can compute both perturbatively higher, and I'll describe why something is going on down here. And these are also, so the other thing, these experimental things are what has come from our personal analysis of this open data. So these are purely, so there's been no unfolding. This is just it should be taken with a huge grain of salt, and it's being done much more precise. So this has now been measured. It's not published, but by both CMS and Atlas very precisely. And then it'll be easier to compare, and the calculations be done at higher orders. Yeah, but absolutely. And so one of the reasons why it's disagreeing so this is related to actually two parts of your earlier questions. So one of the reasons why it's disagreeing a bit, so the first is a physics reason, which is, of course, these are not, or jets are not perturbative over their entire evolution, and they exhibit some confinement transition, where you transition from kind of an evolution in terms of quark and gluon states, where you expect their correlations to be described by these particular anomalous dimensions, and at some point you have confinement, and then you just have freely floating hadrons going off into your detector. And so you expect, since these are just looking at things as a function of the scale, that you should be able to directly see this confinement transition when you measure these 2-point correlation functions. And so before I was always cutting off onto this side of the plot, and so you can see that at this particular scale, scale here, you can see you have this nice perturbative evolution that goes, these correlations build up with the scaling behavior, and then you have a very sharp transition, and on the other side you have freely, essentially propagating hadrons. And so it's actually very easy to compute what the, if you just have some uniformly distributed hadrons, they have a particular power law for this correlation function, which is just essentially geometric. And so you can test that these hadrons are, for example, just uniformly distributed at very small angles. And so if you didn't know before that confinement happened, one could see it kind of very clearly here. And so the other thing which is related to your question is so this is just a log plot of the same thing multiplied by a Jacobian so that it's almost flat in the perturbative region. And so you can see up here that something goes horribly wrong, which is just where you hit the jet axis, or the jet radius. And so here we use like r equals 0.5 jets, and so you can see that it has this universal behavior in here, and then this very sharp drop where you just hit the boundary. And so that's where this approximation that we're using of being able to factorize into these different states is breaking down.
Is there physics of confinement in this picture? I mean, apart from the fact that these are not trying to use a grid, but it's in this form.
Well, so this is what I would like to. So I can. This is what I would like to know how to, for example, see linear in this region. So right now I have no idea of how to compute in that region, and I would love to know how. So here I can compute from the perturbative side, and it blows up. This side is just a free scaling, and so what I would like to know is how to compute in the middle. I don't know how to do that, but I would love to know how to do that, or any ideas of how to even like approach that. And so later on, I'll show like for these 3-point correlation functions, they have a 2D shape, so you can kind of look at them on a plane, and you can again plot this as a function of the overall scale, and you'll see that at some scale it just kind of washes out all the correlations from the hadronization. And we made some YouTube video of this, which if you're bored, you can watch. Okay, so these scaling behaviors, and I'll pick up, or I'll just skip to the end at some point once I run out of time. But so these scaling behaviors are kind of the most basic prediction. But of course, what one would also like to compute is higher point correlation functions of the energy flux. And so this is something just like in the CMB, you kind of start with 2-point correlations, but then obviously kind of more interesting features are in higher point correlation functions. And so of course, these are being computed in the CMB, again, also by Malacina originally. And so one would like to understand if you can compute higher point correlation functions of the energy flux. And so this is interesting both kind of just phenomenologically, because it's something you can directly measure, but it's also interesting just for understanding the general structure of these correlation functions of the energy flow operators. And so the only calculation of multi-point correlation functions of these energy flow operators was done in this original paper by Hoffman and Malacina, where they computed the generic endpoint correlation function at strong coupling using ADS-C of t. And so it's an expansion in the infinite coupling limit. And so it's kind of uniform distribution on the sphere at infinite coupling, and then they compute by essentially viewing these as just some shocks in the bulk, an expansion. And so of course this is kind of an amazing calculation, but at the kind of energies you're going to measure things at the LHC, you're going to be measuring this on perturbative quarks and gluons, and so it's going to be very different than kind of this uniform distribution. And so surprisingly, there's actually been 0 calculations of these higher point correlation functions in perturbation theory, even though using kind of modern perturbative techniques, it's actually quite simple to do. And so I'm not going to go through all the details, but I just wanted to show kind of why it's actually very easy to compute these objects in perturbation theory, and that they give kind of nice results. And so what one wants to do, so these now objects, if I have some 3-point correlation function, I can rescale it and put 1 point at 0, 1 point at 1, and 1 point at some complex value z. And what one wants to compute is just this correlation function as a function of this complex variable z. And so the reason why this is actually quite easy to do in perturbation theory is that what you need to do is to take some splitting function or some amplitude, which produces, for example, these 3 particles, and then one has to integrate them against some particular weights from the detectors against the conservation of momentum delta function for just how these particles go in. And so the reason why this integral is actually very simple is if I take just for a kind of toy example, if I just have some Mandel-Stamm invariant, what you get is some integral here where you integrate over the energy fractions, because the angles are completely fixed by the correlators, of some, if I just expand this Mandel-Stamm out in terms of the energy fractions and the angles on the sphere, which are just now in terms of these z variables on the previous slide, what you get is an integral of this form. And so this is actually immediately recognized as a Feynman parameter integral, where I now reinterpret these energy fractions as Feynman parameters. And so this is kind of a dual description of standard momentum space integrals, where you essentially exchange the external momentum for these differences of coordinates. And so you can just essentially remap these as known Feynman parameter integrals. And so essentially what you do is you take your original correlation function, which has some shape, you can then make some dual Feynman diagram, which in this case is some 1-loop 3-mass box. And then the structure of these integrals is very nicely understood in perturbation theory. You kind of understand what functions appear, and so you can immediately kind of use what has been done on the scattering amplitude side to compute these particular objects. And so if you do this, for example, in n=4, the QCD answer is not that much more complicated, but you get kind of very compact expressions for these energy correlation functions. So this is for the shape dependence, again, as a function of these cross ratios. And so if you're used to kind of seeing these things, these are a combination of these well-known polylogarithmic or particular combinations of polylogams, which also appear, for example, in the correlation functions of local operators. And so these things also, much like scattering amplitudes or correlation functions, have kind of very elegant mathematical structures, even though they're very little explored. And so I think it's worth to kind of perturbively compute them quite a bit more and understand which structures emerge.
Sorry, just to clarify, perturbative in GM is?
Exactly. So this is the first order contribution. And so there's nothing known kind of beyond, this is the only calculation of these. And so it's now been extended to full angles, but it's never been done to higher orders in the coupling.
But do you expect LHC's case to be described by this perturbative limit or no?
So I'll show you, you mean, do I expect the data to be described? Yeah. So it'll be described relatively well, and I'll show that in a second. It will obviously have corrections, but one can go to quite high energies where this will dominate the shape. And I'll show that in a second. Yeah. And so the neat thing with these is that one, unlike just kind of normal amplitudes, which you can't actually like measure the amplitude, here you can just directly go to measure this correlation function and compare it with the calculation. And so this is a calculation of this 3-point correlation function of these energy flow operators inside hydrogen jets. So it's now plotted as a function of two kind of angular coordinates which describe the shape. So for example, down here, you have some kind of compressed triangle, I don't know what you call it, but like this. Here it's this like squeezed triangle, and up here is some equilateral triangle. And so you can actually compare this directly with this calculation. If you overlay them, they're good to within, I don't know, 5% or something. And so it really illustrates that one can actually kind of measure these multi-point correlation functions in real-world data. And so how much time do I have?
We started 5 minutes late, so
I have 5
let's say you have
minutes.
15 minutes. No, we
Oh.
didn't have 15 minutes.
Oh, okay, good, okay. And so one thing which is kind of neat, which one can do, is one can kind of compare these to a huge wealth of calculations of correlation functions, for example, in non-Gaussianities. So there you can also look, and people have done this, for example, correlation functions which are just from some kind of fluctuation as compared to from some kind of classical propagator. And so of course, in the QCD case, what you expect, since you have some particle coming in to produce your jet, is that it should look a lot more like this classical case. And so one can kind of explicitly do this by, for example, putting some toy function which just has a particular propagator like this, as compared to another toy function which is kind of like putting like higher derivative corrections into the inflation case. And so if you compare it to this, you'll see that it's almost exactly like this particular case here of having just some kind of propagator structure. And so you can see that it's not just kind of some fluctuation, but it's actually caused by the LHC, which is of course what you would expect. Okay, and so the reason why these things, at least to me, are quite nice is that they're kind of directly measurable correlation functions which live on the sphere. And so these actually have most of the nice theoretical properties of standard correlation functions, but in kind of a real physical observable. And so you can kind of do things like move them into OPE limits and test that they actually behave as kind of you expect correlation functions to. And so this is very different than, for example, scattering amplitudes, where the amplitudes are of course very nice, but when you put them into cross sections of the LHC, they become some large kind of numerical mess, and you can't really test their nice properties. And so one thing which one can do, which is kind of cool, at least for myself, since I hadn't played with these before, is one can actually perform kind of conformal block decompositions of these objects. And so in this case, they're called kind of celestial blocks. And so what one can do is to essentially expand the original correlator in terms of some, you can kind of think of it as either like a Fourier expansion, or in terms of some particular partial waves which describe the effects of kind of Lorentz symmetry on the celestial sphere. And so you can just expand it in terms of some perturbative data, which is these coefficients, and then some forms which are fixed by symmetry. And so what one can do is one can derive the particular structure of these blocks by studying the action of the Lorentz group on the celestial sphere. And so in particular, we'll have some quantum numbers under the boost along the particular direction of the detector, and then quantum numbers under this rotation. So these are of course just related to these collinear spin and transverse spin, which I described earlier. And so if one actually wants to do this on the full sphere, it's a bit more mathematically intensive, but you can kind of completely do it. But in this jet substructure limit, it's actually pretty obvious what you expect to get, because you can kind of think of expanding the sphere, and if you're just looking at small angles, it's essentially a 2D plane, where what these act as is the kind of boosts act essentially just as dilatations, and rotations are of course just rotations in this plane, and so you expect that what you should get out are just the standard 2D global conformal blocks. And so you can kind of go through the exercise, I won't show it here, but you can just do this in the standard way by solving some Casimir differential equation for the action of the Lorentz group on the sphere, and what you find are exactly just these standard 2D conformal blocks as you would expect. And so these are just some known hypergeometric functions which encode essentially you can just think of them as a particular class of partial waves. And the thing which is kind of neat is that these are just partial waves which are actually living on your detector. So if you plot them, they're just kind of some particular shape like this, and so these ones have, for example, transverse spin, which is why they have some oscillation in this angle here, whereas these ones do not. And so what one can do now is instead of compute this thing directly from perturbation theory, if you just have some data for the particular coefficients, you just kind of add these up, and you expect that it converges quite rapidly. And so this is, of course, what people do for the conformal bootstrap, and so now one can actually apply these kind of directly to calculations of jets. And so it's hard to kind of do it in the full surface, or to kind of observe, or look at it, or how it converges for the full surface. But if you plot kind of slices of this is for like a gluon jet, so the full calculation is up here. And then this is showing in green, if you just put in these twist 2 blocks, which are the leading blocks, and if you add in one additional block, it essentially converges pretty well. So instead of having to compute this full shape perturbatively, it's almost essentially completely fixed by Lorentz invariance up to the OPE coefficients of these twist 2 and twist 4 blocks. And so it kind of allows a very different way of trying to expand, for example, higher point correlation functions in jets at the LHC. And so there's other kind of fun things which one can do with this, because there's kind of an interesting interplay between the structure of this kind of symmetry constraints and the structure of individual Feynman diagrams. So for example, in QCD, you can take a particular diagram like this, where you squeeze together at the OP limit, for example, these 2 quarks. And so of course here you kind of know beforehand what state you're going to squeeze onto. So in a generic non-perturbative theory, you just go onto all particular states, but here you know you're just going to find a particular gluon intermediate state. And so in particular, this has some fixed transverse spin just coming from the spin of the gluon, and so you know that you can only have this particular operator contributing. And so if you look at, for example, the highest transverse spins, you just take this complicated expression we had before in terms of polylogarithms, and if you expand it out and look at these particular pieces, which are coming from here, you'll find that these coefficients of like 6 7s, 5 7s, etc., are just completely fixed by this expansion of this particular 2f1. And so there's kind of an interesting interplay between the calculations in terms of these polylogarithms and nice functions, which control things in perturbation theory, and these generic symmetry constraints, which is how one does it from a kind of CFT or OPE perspective. And so there's some kind of very constrained structure here, which I think is worth exploring more. And so though I won't describe in any detail, I just wanted to mention that one has all the kind of generic properties, for example, crossing symmetry of this OPE. And so for example, in certain channels, you can consider, for example, performing an OPE in this channel, and then an OP in this channel, and they have to kind of give the same answer, and you can play all the standard games of the bootstrap. And so in particular, one can consider, for example, high spin expansions and this Lorentzian inversion, and really start to kind of play much more interesting games to understand the structure of these objects. And so there's kind of an interesting, at least to me, interplay between some of these techniques, which are seemingly very formal, but actually in these kind of nice white paper on the analytic conformal bootstrap explicitly mentions these applications to jet substructure and QCD. And there's kind of like real new calculational techniques which are coming into actual phenomenological calculation.
Sorry, just to clarify, do you mean this bootstrap on the celestial CFT?
Yeah, I would just say a bootstrap of these correlation functions of operators. So one doesn't need to know if there's a celestial CFT or anything. These are just, because you have this OPE, it's just these correlation functions of light ray operators, and one could, or for example, in the high spin limit, one can solve this crossing equation. So it's much less explored, but you have most of the properties that you do of normal correlation functions. And so, for example, I'll probably skip it here, but one can do this kind of Lorentzian inversion and show that it's analytic now in this transverse spin properties, and so they have a lot of the properties of local correlation functions, even though they're these kind of correlation functions of light ray operator.
But in terms of this variable, like the cross ratios will be constructed out of these variables.
Out of the angles. Exactly. Yes. So I'll skip this. And so I should just say that these have had actual kind of impact on very phenomenological kind of simulations for the LHC. So of course, for generic searches, what one uses are these kind of parton shower programs. And so one of the things which came out of understanding the structure of these operators are the kind of transverse spin properties of these operators. So in particular, I showed earlier these transverse spin operators, where if you kind of take, for example, a 3-point correlator and spin 2 of them with respect to the other, you can excite an object which is exactly the spin of the gluon, which I just showed, which has an actual kind of physical imprint. And so this was something which was not understood how to do before. And so now that one has kind of analytic calculations and an understanding of how this can work, it's now being put into the kind of simulations which are used at the LHC. And so one can hope that one can actually have kind of things going from these like formal CFT developments into actual kind of general searches at the LHC. And so it's having kind of a concrete impact. And so I just wanted, this will just be essentially one more slide, but once you have these things and understand them in kind of simple systems like the LHC, what you obviously want to do is to use them to probe more complicated systems. And so one very complicated system is the quark-gluon plasma. And so what we would like to do essentially is to kind of shoot, or so one way of understanding this quark-gluon plasma is to shoot, for example, a quark or gluon through it. And so in reality, what you're doing is producing an center and some collision and it comes out. But one can just imagine instead that you kind of shoot it through, and then what it will do is to produce some jet, and what it will do is imprint the internal structure or kind of internal scales of the quark-gluon plasma into some particular features in this correlation function. And so if you understand the structure of these correlation functions in vacuum, and they mostly just have these scaling laws, then anything, any kind of internal scale of the plasma will just be imprinted at some particular scale in the correlation function, just like the hadronization scale was imprinted as some very sharp feature.
Sorry, a very naive question. I'm not an expert on it, so sorry if I say something stupid. But what other observables you can get more than the shear viscosity and this kind of entropy per unit of particle that usually the people know how to compute in other ways?
Yeah, so I'm also not a very big expert on the heavy ion, so this is just something I'm kind of playing with. But there's a bunch of things one just kind of wants to understand how these things behave as a function of scale. And so those are kind of very global properties of the plasma. But by looking at kind of subscales, you can look at how the plasma behaves at different scales. And so in particular, what you want to kind of see is how it goes from some kind of bulk properties to being an asymptotically free set of quarks and gluons. And so the way you do this is by kind of using these jets to probe it at different scales. And so from that, you can kind of characterize the structure of the plasma. That's the kind of very basic idea. And so here I'll just show kind of one example of how one can kind of see it. And then, I mean, this is something I've just kind of started looking at, so I probably know less or more or less than you. Less or more, yeah. But the kind of idea is you just want to probe the plasma at different scales and see how it responds as you kind of ping it at different scales. This is the kind of very, very lowest order idea. And so what you can do, just for example, with this 2-point correlation function, is that now you have some scale. You can think of this as essentially characterizing, at least if you just think of a kind of 1 to 2 perturbative splitting process, is essentially characterizing how long this particle lived before it kind of split into the 2 particles. So it's just kind of its like lifetime. And so if you have a very small angle here, it means this thing lived for a very long time and just kind of came out of the plasma and then split into 2. And as you kind of move this angle up, you kind of force the particle to go back into the plasma. And so what you expect is you kind of essentially will see the scale of this ball of plasma imprinted into the structure of your correlation function. And so as you kind of increase the angle here, you see this nice scaling behavior, which is exactly the same as a QCD. And then you immediately see the kind of scale of the quark-gluon plasma. And if you convert this into some actual dimensional units, it's just like a 10 femtometers or something. And so you can see very clearly the kind of structure of the kind of microscopic plasma. And then ideally, you can use different models of the plasma to understand the interactions in this particular region. And so you're kind of probing the interaction with the plasma at some particular scale shown here.
Is that data? I can't read.
No, that's just some,
okay.
yeah. So it's being done in data. That's just some toy calculation. Okay, so just to summarize, so hopefully I convinced you that some of these insights from formal theory are having an actual impact on how both one does calculations at the LHC as well as how one analyzes the data. And the thing which kind of makes this possible is that these jet substructure analyses provide kind of a physical realization of this operator product limit of light rate operators. So people are really often studying the case where you have a kind of a very small jet and are bringing a bunch of these operators together. And so this kind of provides some form of bridge between all these nice formal theory developments and QCD phenomenology. And hopefully this will have kind of impact going forward. So thank you.
Okay, there's been a few questions, but for sure this time. Go ahead.
A question of this OP. If I understand correctly, the way it works, it's you get again these O's, again line integrals of some.
Exactly.
Yes. But is something it should be obvious a priori or not? Because for me it's not obvious when you.
It's not. I'd say it's not obvious, and also at like higher twist. So the thing that makes it computationally, or why the higher objects are not as understood, is you can get, like, let's say if you wanted to go to twist 4, so now you can have 4 fields which are smeared across along the light cone, and you can have some non-trivial kernel, because now they can have more relative distances between them. So if you just have 2 operators, it's essentially like fixed how you do this, and it's a very easy smear. But once you get multiple fields, you can have some much more complicated kernel. And so it's kind of, if you have like 2.
So it's not guaranteed that it will be integral of the local operator.
No, and it's not integral of a local operator in general. And so that's been like definitively. And so in general, what one expects, like if you have some kind of like 2 of these, which are integrals of like some operators here, that this is some integral of like, you can now have multiple fields sitting at different points with some like an integral against some more complicated kernel. But just so that it is some, and so they become kind of increasingly smeared as you go to higher orders in the expansion. But the ones with 2 operators are now kind of quite well understood, and so they do not reduce. So in certain cases, at the integer values of j, they reduce to integrals of these operators along the light cone. But for non-integer values of j, they do not. And so you can think of it as kind of like a residue at integer values of j, but generically at higher orders in the expansion, you get all sorts of kind of crazy integrals of multiple fields along the light cone, and that's where it's kind of less explored. And so this one, when it's taking advantage, that you just get these specific things you understand quite well.
So you have these parton shower applications and quark gluon plasma, but you also mentioned your last point, I think, in your summary slide, is applications for new physics. So what do you have in mind specifically? How does this?
Yeah, so I think it's kind of, in my mind, kind of a multi-step thing. So one of the, I think now the way that most of these searches are done is with some form of just machine learning, where you just train it on some jet. And so the problem is then you need a very good description of the internal perturbative dynamics of the jet. So these machine learning algorithms are training up to like kind of 10-point correlations and stuff, and they're looking at, like they're explicitly looking, for example, at these azimuthal correlations. So you can test and see if that's done. And so if these things aren't well described in the kind of training samples, then you can't kind of pick them up and exploit them. And so I think what one wants, or the kind of most direct application,
they're not implemented in the
exactly, is to kind of build up these pieces, and then, because ultimately in like real, most real analyses, you're going to have to just use some parton shower. And so is the problem with the reason why one hasn't been able to extend parton showers is one didn't understand these higher order features. And so I think realistically, the way that it will propagate, so I think there's some other kind of examples which I didn't discuss, which are a bit more specific, like these quark gluon plasma, or like looking for this, like some people have used it to look for like CP violating couplings to where you produce some polarized gluons, which then you can detect with these correlation functions. But I think realistically, it's just improving the description of these things, and then it can be implemented in like generic Monte Carlos, which are then you just use whatever machine learning you want. And so I think that's the most direct path.
One way that comes to mind, and I want to know if somebody's estimated the possible sensitivity, is supposing there was a new kind of a Z suggestion which only decayed hadronically. That would be very tough to find with a conventional approach, but you should, I guess, see a distinct discrepancy. And I wondered if anybody might have modeled how big a production cross-section you could have if you mentioned a Z prime that, let's imagine a mass of 200 G.
So somewhere, so this Z prime search, so has actually been, so I'm not an expert, so this is some normalization of the coupling.
No, I don't mean with the standard method. I mean, you hear about people trying to look at internal jet substructure. But this other method is much more general of the energy correlate.
It's much more general, but
I'm just curious if anyone has
no,
explored
so
how.
one of the problems, or one of the things that makes it difficult to directly apply is when we need to change a little bit how one does the analyses, because it's done on a statistical ensemble instead of event by event.
Yeah.
And so one could look at some, and this is just not something that people have ever tried. It would be super.
You've convinced.
Yeah, it would be super cool to try, but it just kind of changes how the analyses are typically done.
Yeah, but you could run a simulation to get an idea.
Yeah. No, it'd be very, and I think
I mean,
there's.
it could be that it's hopeless. That
Yeah,
you
yeah,
have too much sensitivity.
Yeah, no, it would be very interesting to try, and I think hopefully someone, will do it. But I don't have a kind of concrete, because it just kind of changes how they're normally done, always with these kind of cut and count and stuff. So it just, you have to do it a little bit differently and look for some structure appearing in the multi-point correlator. But it would be super cool if one could do that. Absolutely.
Any more questions? For Sangi again?
I mean, it seems like it would just be a characteristic scale.
It would be super. Yeah, and so one can do it. So, like for example, for samples of like top quarks, you can like see the top appearing and as like a clear bump. And so I think it would be
Doing it with
You need to fix it. You need to fix it. They won't fix it.
Yeah.
They might
It's
send
not
it to
generic
the
to ask
referees.
if there would be something like a top.
Absolutely.
That might be a good place to
It would be
start.
super cool. It's just partly it's like a sociological thing that everyone does like analysis in one way, and here you'd have to just.
The files that work.
Yeah.
It has to compile correctly.
Yeah,
It's just the editor will fix
that's
it.
true. Yeah. No, it would be fun to do.
It would be very, very interesting.
It would be, yeah. So there were these people from, unfortunately I forget, these postdocs from EPFL. They were using these a little bit to look for they were using these like spin correlation ones to look for something. I would need to build up their paper, but they were looking at some statistical ensembles and looking for like shifts. So there was looking for something with an enhanced, more like with particular CP properties, instead of looking for mass volumes.
Right? So that's what the editor receives and the
Yeah.
editor will send to the
But
referee.
no, it would be super.
Because sometimes I find
It would be super cool.
because they don't have review and I just
Well, you need to find a nice, where you could beat something that's already being. That's the problem. Is it's hard to beat
after
some of these where you just feed it into like a machine learning
Right, a
thing.
mass bump is so hard
there I can't have
because
the
there's so
previews.
many
Oh,
combinatorics.
okay. Yeah, but
Exactly.
Somehow just
Exactly.
through that.
Exactly. Yeah. Yes. No, I agree.
Well, it's
Your
fun,
questions,
but,
it's very counterintuitive, and that's part of the reason why it was like it was when like Maldacena explained it was not understood by the phenomenon community like what they were doing, and because
It's astonishing that it's been 12 years when he's so
It is-
influential.
exactly.
And it seems like such an obviously great idea once it's articulated.
And also I didn't mention, but I don't know. There's this person Steve Ellis.
Yeah.
So he actually originally did
The guy at Washington.
Washington. Yeah. So he essentially said that this is the way it should be done in 1970. I don't know.
Really?
Five.
Yeah.
This was just completely lost to. And so I showed it to him, and I think it is completely it's how it should be done, and it just for some reason it went off in this.
Some sort of sociological.
It's a purely
Well,
sociological.
it's the sort of thing that I could imagine in the end, it wouldn't be as sensitive for some reason, because sometimes, when you have some sort of understanding, you gain signal to noise somehow. But always but here what's so powerful in principle, it seems, is that there might be just so much there that you're not.
Exactly.
Then you have the benefit of lots of
Exactly, and
statistics.
especially now one can actually compute these higher point correlations, and that's just something that's not possible with older
Also.
observables. And so then you can start looking are you sensitive to things that only imprint themselves in higher point correlations, and it's just no one has done that, so it's I don't know.
Yeah, the most interesting, at some level, you'll hardly get a huge, some part of the community will be motivated by testing our ability to do perturbative QC.
Yeah.
But there's a lot of other people.
Exactly.
For
No,
whom that won't.
absolutely,
get them going.
absolutely. And this is what
Obviously,
also like partly the like nuclear physics community is also quite interested in them.
I bet it's useful for the EIC.
Exactly. And so you can see things very cleanly because essentially what all it does is it just detects whenever there's a scale.
Yeah,
So you can see like hadronization, you can see
yeah, that's.
nuclear, and so from that perspective, so I hope to appeal it to also eventually beyond the standard model people, but I think the ones where it's an easier sell is nuclear.
Looking for scales from non-perturbative.
Exactly. And that's what they love to do. And that's very, if you use like standard observables, they're all like smeared. It's a very not clean, whereas these are much cleaner for that type of thing.
Yeah. Well, good luck. Thank you very much.
Actually, sorry, I don't know if I've ever.
Oh, I'm Glennis Gerard.
Yeah, okay, that's what I thought.
Did
Yeah,
you-
I'm Ian.
Ian,
Ian
what's
Moult.
Moult.
Yeah.
Your
no,
name
nice.
appeared a lot, but
Yes, yeah.
I didn't see your name.
Yeah, no, thanks for the question. They're very good. Yeah.
I wanted to ask you about this bootstrap approach. That you
Sure,
said.
yeah.
Did you have in mind just two-point function of these correlators, or because
Thank you. Maybe I'll see you later.
Yeah, okay.
My office is over there.
Oh, okay.
because are you imagining like really 4-point function of these energy correlators? Because that would be very hard. Also, like the 2-point functions are not fixed, right? Even just the 2-point function of the energy correlators,
So
they're not fixed.
good.
Yeah.
So this is good. So, well, let's make sure.
Because the 1-point functions are non-zero essentially,
Could be listening.
Ivan is probably